Hello and welcome. In this video, we're going to take our first look at neural networks. We will go over a little bit of history, then look at the biological inspiration for neural networks. Follow this up with a discussion of how neural networks can mimic nonlinearities present in data. We will discuss the simplest neural network architecture possible and take a deep dive into what kind of input-output relationships it can construct. And we will apply this simple neural network model to a regression problem. Finally, we'll add a little bit more complexity to that simple neural network, and we'll see how we can do better. Finally, we'll look at an example where we use a Python library called scikit-learn, and we will implement a neural network to fit a neural network model to highly nonlinear data. All right, so to begin, if you've ever wondered how computers can do fascinating things like recognize images or understand speech, or even play complex games like chess, then the answer really lies in the fascinating world of neural networks. So as I mentioned, in this module, we'll take a deeper look at the architecture of these networks and how we can build intricate relationships between the input and the output. An important thing to mention is that neural networks are incredibly versatile and scalable, and they are really tackling some of the most challenging problems we have right now. You are all familiar with um, AlphaMind playing chess. You're familiar with several examples of object detection or image segmentation. And it also turns out that several of the generative AI models out over there are built upon the basic backbone of artificial neural networks. And so while they might seem like a modern marvel, the basic concepts date back to 1943 with the McCulloch and Pitts model. And I have an interesting snippet about Walter Pitts in this Jupyter notebook. Uh, Turns out that he was one of the brightest minds of his generation and did not uh, get a formal degree, but was involved with several mathematicians at that time. In fact, the movie Good Will Hunting is based off of his life. All right, so with that background, we'll look at what a biological neuron looks like. This is the construct of a biological neuron. You have multiple dendritic branches which connect to other neurons upstream from where signals come through the connections. The connections are electrical connections or chemical connections or both, and they pass through these dendritic branches. So the signals come in, they're either attenuated or amplified in these branches. And finally, if they exceed a certain threshold, then we're going to be sending that signal downstream to more neurons along the way. So that's what a biological neuron essentially does. And we mimic the function of a biological neuron with an artificial neuron. And an artificial neuron looks something like this, where we have an input, and the input is fed to what's known as a neuron in a hidden layer. And at the hidden layer, we send the signal forward if the signal exceeds a certain threshold. And finally, we output the result in an output node. So between the input and the hidden node, we are going to multiply the input signal with a certain weight. Now the weight can be larger than 1 and we can amplify it, or it can be less than 1, in which case we attenuate the signal. And we also add a bias. which essentially shifts the signal up if it's a positive bias or shifts it down if it's a negative bias. Then it goes to the hidden layer. And in the hidden layer, we have something called an activation function, which introduces nonlinearities in the input-output relationship, and we'll see that in a minute. But it also performs an important function. It only sends a signal downstream if that signal exceeds a certain threshold. And if the signal exceeds a certain threshold, then we're going to be outputting potentially a non-zero value, which is again scaled based on some weight going to the output, and again shifted up or down based on some bias. If the signal does not meet the threshold, then the only value that's passed on is a value of 0. So let's look at what this activation function looks like. So we're going to be discussing something called the RELU activation function, which is one of the most common activation functions. So this is a video which shows you what the RELU activation function looks like. On the y-axis, I'm plotting the RELU function as a function of the input x, and this is the x-axis. So you can see that for negative values of x, the output of the RELU function is essentially 0. And for positive values of x, the output is x. So essentially, the slope of this line is 45 degrees. It's a 1:1 line. And this RELU function is really useful for us and one of the most commonly used activation functions because it's simple. And secondly, it introduces nonlinearities. What do I mean by that? I mean that for values which are negative, the output is 0. For values that are positive, the output scales according to the input. So we're creating a nonlinearity in the input-output relationship because of this change in slope located at 0. The second reason why the RELU function is very popular, and we'll see this later on when we deal with deeper neural networks, is that the gradient or the derivative of the function is nothing but 1 when x is positive. It's 0 when x is negative. And this has important implications when we deal with very deep neural networks. But before we jump into very deep neural networks, let's look at the architecture of the simplest neural network possible. And before we do that, let's finish watching this video, which shows you how incoming values of x are sent out according to where they lie on the activation function. Positive values are sent out as positive values. Negative values are sent out as zeros. So you can see that unless the input exceeds a certain value, it's not going to be sent to the output cell. All right, so let's look at the simplest neural network possible. And the simplest neural network possible is what we have already seen earlier, which is one input node, one hidden neuron in one hidden layer, and one output node. All we're going to be monitoring is the output node, and we're going to be feeding some numbers or inputs to the input node. And that's the reason why this is called a hidden layer. We don't really tap into this or monitor this. It's hidden from view. We can have multiple hidden layers and multiple hidden neurons, and we'll see some of those things in this lecture as well as in subsequent lectures. So let's look at the operation of the simplest neural network, which is one input node, one hidden neuron, and one output node. So for a given input, in this case, the value of x is 0.7, I'm going to feed 0.7, I'm going to multiply it with the value of 2, and I'm going to add a bias of negative 0.5. And then I'm going to send it to the hidden layer. You can see that the RELU function, activation function, is embedded in the hidden layer. And then we'll see what happens as it moves along to the output. The other thing I want to mention at this point in time is that I have arbitrarily chosen these weights and these biases. We'll see how these weights and biases are chosen at a later point in time when we look at something called backpropagation, which allows us to calibrate these weights and biases and get a neural network to match data. So the output from uh, uh, the output or the input into the hidden cell has a value of 0.9, and zero point 0.9 goes in. It's sent through the activation function, RELU activation function. And since it's a positive value, we're going to get an output of 0.9 from the hidden neuron. And that's multiplied with a weight of 1.5, and we add a bias of 0.2, and we get a value of 1.55 on the output side. So you can see that for any given X on the input side, we can go through these calculations and estimate what the output is going to be. We can, of course, repeat this for different values of X, and we can also plot what the outputs are going to be for those different values of X. If we did that, then for different values of X going between 0 and 1, for that simplest neural network that we just saw, the output is going to look like this. And you can see that this is a non-linear input-output relationship. We have non-linearities because we have a change in slope at this specific location. Now, where this change in slope occurs depends on what kind of biases you are using in your neural network model. We chose some biases entirely randomly, and that's the reason why there's a change in slope at this location. If we had chosen a different set of biases, we would get a change in slope at some other location. Also, the height of this segment over here also depends on the biases, and the slope of this line depends on the weights we have chosen. All right, so let's see our first neural network in action. It's a simple neural network with one hidden layer containing just one neuron. Here is the Python code for that. We are creating a function to model the performance of an RELU activation function. If X is positive, we return the value of X. If X is negative, then we return a value of 0. And here is my neural network. The inputs are the weights, W1 and B1, which go from the input node to the hidden layer. And then I have the weights W2 and B2, which go from the hidden layer to the output node. So when any input X comes in, we multiply it with W1 and add B1 and send it through the RELU activation function. And we're going to get the output from the hidden layer. We take the output from the hidden layer, multiply it with another weight W2, and add another bias B2, and we get the output of the neural network. Over here, I'm just going to randomly initialize the weights and the biases to be some values. For instance, the weight going from the input to the hidden layer is 1. The bias going from the input to the hidden layer is negative 0.5. And the weights for the output coming from the hidden node is 1. And the bias associated with the output is 0. Again, these are randomly chosen. What we're going to do now is we're going to run this neural network, and we're going to plot the output of this neural network for different values of input. ranging between 0 and 1. And when we do that, I should have first started with all of the other cells. So when we do that, we get the output versus the input values of X. And the blue line over here depicts what the neural network is predicting for those different values of X. For example, if the input is 0.8, then the predicted value of Y is approximately 0.3. What I have in these red points over here is what my data looks like. Or in other words, if I'm trying to uh, take a neural network and fit this data, then my goal is to get this blue curve to be as close as possible to the red data points in my training phase. And so what I'm going to do is I'm going to adjust the weights and the biases in some fashion so that my blue curve more closely matches the red curve. And this is what we do in regression. So since I've built my own neural network, I'm going to manually adjust the weights and the biases a little bit. So first things first, I can see that I should probably move this kickoff point a little bit more towards the left. So let's see how we can do that. And then later on, we can adjust the weights. So maybe I'm going to change my bias a little bit and make it maybe negative 0.2 and run this and see what we get. And you can see that now there's a change in slope at a value of 0.2, and then I have the curve going out. It's a decent match to the data in comparison to what we had earlier. We can fine tune the weights a little bit more so that we get a better match. For instance, if I change the weight to be about 0.9, you can see that things are going to change a little bit. And in fact, there's quite a bit of mismatch. The mismatch increased. I needed to increase the slope rather than decrease the slope. So let's make it 1.1 instead and run this model. And when I do that, you can see that the overall match is significantly better than what we had earlier. And in this fashion, I can try and change the different weights and the different biases to best match my data. Of course, keep in mind that we are working with a very simple model. We would not be able to match the data perfectly. So the second thing I want to point out is that we are just visually inspecting the match. We're not doing any training and testing to see how well the model is matching the data. The reason why I'm doing this is because we're just illustrating what happens when we have one single neuron, or what does one single neuron do to our input-output relationships when we are trying regression. All right, so if one model fits the data reasonably satisfactorily, then let's see what happens if I had two neurons. So I have the input where X comes in. X goes to hidden neuron 1 using some weights and some biases. And X also goes to another hidden neuron in one hidden layer. This is one hidden layer containing two neurons. And I have the corresponding weights and biases going to neuron 2. And then from over here, I'm going to have a weight that multiplies the output of hidden neuron 2. And then another weight that multiplies the output of hidden neuron 1. And then I add a bias to both of these. And finally, I get my output. Okay. Of course, keep in mind that in the hidden neurons, we still have our activation functions. We'll see how this works. So we're going to illustrate that with a video. I have two hidden neurons. This is the architecture of my neural network. I have two inputs, or sorry, one input, but two connections to two different hidden neurons. And from there, a connection to the output. So one of the connections is going to take X, multiply it with 1, and add a bias of negative 0.6. and the output from the first hidden neuron is going to be sent through the activation function to the output. Coming from the input to the second hidden neuron, we have the corresponding weights and the activation function. So I multiply the input with a value of 1, add a bias of negative 0.2, and then I have the activation layer acting upon that value and then send to the output cell. So you can see that now I'm taking this weight 1, multiplying it with the output of neuron 1, and then a value of 0.8, multiplying it with the output of neuron 2, and then adding the bias, and I finally get my output. Again, the weights and the biases are entirely randomly chosen. So for different values of x, I can plot what the neural network is going to predict. Again, I'm going to examine what the neural network predicts for values of x between 0 and 1, just for illustration purposes. So we can see what happens with just one neuron. If you tap into the output from neuron 1, we get this specific curve. The slope depends on the weights going into neuron 1, and where this kicks off depends on the biases in combination with the slope. We can also examine what's the output from neuron 2. That's given by the second green line. And finally, we can see what happens if we add them both up and multiply them with weights and then add a bias. We get the output from the artificial neural network, our simple artificial neural network. I want to spend some time at this specific point in the video and examine what we're seeing. So you can see that the output of the neural network is the sum of the output from neuron 2 and neuron 1. Both of them are 0 over here. So the neural network output is exactly 0. After that, the output from neuron 1 continues to be 0. It's 0 because of the chosen weights and the biases going to neuron 1 and coming out from the hidden neuron 1, while hidden neuron 2 has some positive value. And so the output from the neural network is pretty much whatever neuron 2 is telling you. And then finally, at a value of x equal to 0.6, I have neuron 1 also being activated. And so the total output is going to be the sum of the outputs from neuron 1 and neuron 2. And because we are summing up the outputs from neuron 1 and neuron 2, you can see that we have 3 segments in our output. On the yellow line, we have 2 changes in slope. So potentially, if you have 2 hidden neurons, you're going to have 2 places where the slope changes. And you can see that this function over here that we created is more nonlinear than the function we created with just one neuron. So just to recap, the artificial neuron network output is the sum of the output from neuron 2 as well as the output from neuron 1. Let's see this in action using Python. So I have the same ReLU function. I have the same neural network, which takes in the same arguments. And I'm going to specify some weights going into the hidden neuron 1. I'm going to specify some weights coming from the first hidden neuron to the output. Some weights going into the second hidden neuron, and a weight coming into the output layer from the second hidden neuron, and a bias for the output layer. With these weights and biases, let's see what happens when I feed a specified value of x ranging from 0 to 1. I should make sure that I run all my cells. Okay, So I've generated two plots over here. Let's examine the plot on the right. The plot on the right shows my neural network output, and the points in red represent my data. And you can see that the neural network output is quite different from what my data is telling me. And so there are large discrepancies. I need to match my neural network model to my data. That's the process of training. The other thing you can observe over here is that even though I had two hidden neurons, there's only one change in slope. And the reason for this is because we're only examining input values between 0 and 1. There probably is another change in slope happening to the left of this graph, which we're not plotting. But if we adjust the biases and the slopes, we're likely to see that second change in slope as well and get a more nonlinear function within the range of 0 to 1. Let's draw our attention to the graph on the left. I have the output of my first hidden neuron, shown in blue, and the output for the second hidden neuron, shown in red. And you can inspect these two and see that the output of your neural network is nothing but the sum of these two neurons. And if you look at the second hidden neuron more carefully, you can see that it probably has uh, a change in slope occurring at values of x closer to maybe negative 0.1 or negative 0.2, depending on the bias. So let's try and match my neural network predictions with my data. So first things, I'm going to try to make the neural network output more nonlinear, which means that I'm going to try to get two different changes in slope. So for that, I'm going to try and adjust the bias. And again, keep in mind that this is entirely trial and error. We're not, I do not know the answer. So we're just going to examine things. From experience, I know that adjusting some of the slopes and the biases in a systematic manner would allow us to get a good match to the data. So instead of a positive bias, I'm going to try a negative bias for the second hidden neuron, maybe a value of negative 0.3, and see where that gets us. So now you can see that the output of the neural network has two changes in slope, and it has three segments, which is what we've come to expect. And you can see the output of the first neuron hasn't changed, but that of the second neuron has changed because we changed the bias into the second neuron. And therefore the composite output has also changed. Maybe a bias of negative 0.3 wasn't good enough for us. Maybe I'm going to move this change in slope a little bit more to the left, maybe make it negative 0.25 and see where that gets us. It's marginally better. The other thing you can see is that the second segment matches our data pretty well. Now, all I need to do is match the third segment to my data. Now, the third segment has contributions from both the second neuron and the first neuron. This is important to note because if I change the slope coming out of the second neuron, then I'm also going to be changing the slope of the second segment, because the second segment is nothing but the output of the second hidden neuron. But if I change the slope or the weight associated with the first neuron, then the only segment that I'm going to be changing is this last segment over here. If we can try that out, if I change the slope associated with the second associated with the second neuron, if I make that 0.5, for instance, you can see that I've changed the slope for both of these segments because I've changed my second neuron output drastically, whereas the first neuron hasn't changed. It appears to have changed simply because the scale on the graph has changed. Okay, so I'm going to go back and make this a slope of 1 and read on this. So this brings us back to where we were. Now I'm going to decrease the weight coming out from neuron 1 to the output layer. I'm going to make it maybe 0.8 as a first guess. And see where that gets us. You can see that we're now closer to the data. I'm going to try maybe 0.6 and see where that gets us. And in fact, this is a pretty good fit to the data. You would be hard pressed to do significantly better than this. And so what I was illustrating to you is the process of training a neural network to match observed data. And we did this by adjusting the weights and the biases. And while we did it with a trial and error approach, in reality, there's a method by which we do this. And that's where we're going to be talking about back propagation and which ones have a greater impact on the output and why the ReLU function is a good activation function. Well, if two neurons helped us to match the data pretty well, what can three neurons do? So if you have three hidden neurons in the hidden layer, then, and the corresponding weights going to neuron 1, the weights and the biases going to neuron 2, and the weight and the bias going to neuron 3, and then the weights coming out from there into the output with the corresponding bias, as well as the activation layers, activation functions in the hidden layers. Let's see what we can do with this. So we're going to play another video. This time around, I have three hidden neurons with their corresponding activation functions, which are the ReLU activation function. An input X comes in, it's multiplied with the weight, then a bias is added to it, sent to neuron 1. X comes in, then I have the corresponding weight and the bias, which takes me to neuron 2. X comes in, I have the weight and the bias, which takes me to neuron 3. And from each of the hidden outputs, hidden layers, I have the ReLU function acting upon the input. And finally, all of these outputs from the hidden neurons are added up, are multiplied by the corresponding weights, and then added up to give me the output. So if I want to plot what happens with the entire neural network, I can see what happens with the output from neuron 1, the output from neuron 2, and the output from neuron 3. And of course, these weights, these outputs correspond to the weights and the biases that we randomly chose. If we had chosen different weights and different biases, they would all look different. But if I add all three of these, then I'm going to get the composite neural network output, which is going to contain three different changes in slope. You can see there's a change in slope occurring over here, a change in slope occurring here, and a change in slope occurring here. And this is a more nonlinear function than what we had with two neurons. So the more number of hidden neurons we have, the more nonlinearity we can create in our output function. So if you have a highly nonlinear function, you can imagine that more neurons would likely do better up to a certain limit. All right, so let's implement this in Python. I have the same ReLU function, the same neural network architecture. And I have some randomly initialized weights. These are the weights coming into and going out of the first hidden neuron. These are the weights coming into and going out of the second hidden neuron. These are the weights coming into and going out of the third hidden neuron. And this is the final bias being added. And now, if I examine my neural network output given by this blue curve, you can see that I have three changes in slope. I have four segments. And with the randomly initialized weights, I do have a pretty good fit to the data already. You can examine the output from the third hidden neuron, from the second hidden neuron, and from the sorry, from the first hidden neuron and then from the second hidden neuron. So where they all kick off and the slopes depend on the weights and the biases again. So I'm going to attempt to match the data with my neural network containing 3 hidden neurons. So the first one that kicks off is my second hidden neuron. I'm going to change the bias associated with that a little bit. Maybe let it kick off a little bit earlier. Let's see what happens. So you can see that the curve kicked off a little bit earlier. And then I have this segment over here. So what I'm going to do is I'm going to adjust the slope of this segment. And this segment only gets contributions from the second hidden neuron. So I'm going to adjust the slope coming out of the second hidden neuron. Maybe make that a 0.9 as an initial guess. And you can see that now we've matched the data pretty well. I'm going to decrease the slope a little bit more, maybe make it 0.85. And we have a pretty good match to the data. Now, of course, this segment over here has contributions from neuron 2 as well as neuron 1. So in order to get this to match the data, I'm going to adjust the slope of neuron 1. And I can also adjust the slope, I'm going to adjust the slope of neuron 1, the blue curve over here. So I need a pretty drastic change. So I'm going to make this about 0.6 and see where that gets us. It got us pretty close to the actual data. Maybe if I tried something closer to about 0.5, I might be very close to what the data looks like. And there we go. A slope of 0.5 associated with the hidden neuron 1 output gets us pretty close to the data. Now I have to adjust the slope over here. I'm going to adjust the slope coming out of the third neuron because this is entirely due to the contributions of the third neuron. I don't want to adjust the slopes of the first and the second because I already have a good match to the earlier part of my curve. So going back to the first neuron or the third neuron, I'm going to reduce the weight a little bit. I'm going to make it maybe 0.7 and run this. And you can see that now I'm pretty close to what the data looks like. If I adjust the slope a little bit more, then I get a pretty good match to the data. And of course, we can tune the weights and the biases and get a higher fidelity match to the data. But for the purposes of illustration, this will suffice. What we're doing is training the neural network to match my observations by adjusting the weights and the biases. In principle, however, this is not how we are going to be doing things. We're not going to successively keep increasing the complexity of our model to match data. And we're not going to keep doing this over and over again. We're also not going to be constructing neural networks from scratch. What we're going to be doing is using built-in or ready-made Python libraries that contain neural network models, and we're going to use those to attempt to match our data. So we'll look at an implementation of such a model in the next Python code cell. Over here, I'm going to be using a specific library that's called scikit-learn, and we're going to be importing something called the MLP regressor model from scikit-learn. MLP stands for multi-layer perceptron, which is another expression for an artificial neural network. We have a data set, which you will see in a minute, but I first need to define a variable that refers to my model. I need to specify the architecture of my model. Specifically, in this case, I'm choosing one hidden layer and one neuron in the hidden layer. So it's not 10 neurons, but it's 1 neuron in the hidden layer. And there are other parameters as well, which we'll keep fixed for now, but you recognize that the activation layer is the ReLU activation layer. And finally, to match or to fit to my training data, I need to adjust the weights and the biases. How is that done? It's done using a specific algorithm, which we're choosing over here. And don't worry about this right now. When we deal with backpropagation, that's when we're going to be talking about this. We're going to take our model and we're going to be fitting it to our data, which is where we tune the weights and the biases and get the best fit to my training data as possible. And then we're going to see how well that model does. And we're going to plot both the model and the data. So let's run this specific cell. All right. So here you can see on the y-axis is my target set of variables or target data shown in these red dots. You can see that it approximates a sine curve. And on the x-axis is my input. And if I were to choose just one neuron, this is the pretty much the best that I can do. Let's try this with a slightly larger number of neurons. Let's try this with maybe 6 neurons. If I tried this with 6 neurons, then you can see that right now I'm able to capture lots of the nonlinearities in the target variable. You can see that I'm matching these red dots more closely with a neural network that contains 6 neurons in its one hidden layer. Well, what if I tried something more complex? What if I tried something like 10 hidden neurons in that one layer? Then probably we might be able to do a little bit better. And you can see that with 10 hidden neurons, I'm pretty much just connecting all the dots and I have a perfect match to my training data. I'm not saying that an artificial neural network with 10 hidden neurons is better than a simpler model. I'm just saying that we're getting a better match. We still need to do our training and testing to see if this is actually a good model or not, or if it's overfitting our data set. But the point I'm trying to make over here is that overall, a neural network with 10 hidden neurons has captured lots of the nonlinearity embedded in our target variable. And that's fascinating. Going from one hidden neuron to 10 hidden neurons, we were able to replicate the data trends very, very well. And that's what we mean by a neural network being extremely versatile and scalable. And it's almost considered to be a universal algorithm to fit most nonlinear functions. So with that demonstration of simple neural networks, just to recap, as I mentioned, neural networks are extremely adaptable, extremely versatile, and can fit functions of arbitrary complexity. And for the purposes of illustration, I just had one input node and one output node. In principle, you don't have to have just one input. You can consider multivariate inputs leading to multivariate outputs. So with that, we wrap up our discussion, introducing you to neural network architecture and how neural networks are capable of mimicking nonlinearities in our data.